Hi everybody. So in today's video, we will be doing some practice problems using the free fall methods. So we'll start right off the bat. We have three example problems that we will go over in this video. So first, we have a skydiver jumps out of a space shuttle as it enters the thermosphere at 500 kilometers above the surface. They jump with an initial velocity of -2 meters per second. The approximate average acceleration for the descent is -9.4 meters per second squared. Their parachute fails and there is no air resistance. How long until they hit the ground? So first, you always want to write down your givens, but I did want to make note of one of these givens. Right here, 9.4 meters per second squared on the average acceleration. Now, as you leave Earth's surface, technically your gravity gets weaker and weaker. Usually that's not an issue for civilians because we usually don't get high enough off the ground for that to matter. But if you're up in the thermosphere, that acceleration due to gravity is going to change drastically. So on average, remember we have to have average acceleration to do these one-dimensional kinematic problems. So the average acceleration from the thermosphere to the ground was -9.4 for this problem. So I wanted to clear that up before we continued. So let's use you. Okay. So let's write down our givens first. Givens, we have a change in position. So we'll use change in y because this is a free fall, right? So change, change in y of -500,000 meters, right? They actually jump downward with an initial velocity of -2 meters per second, and then we have the acceleration is -9.4 meters per second squared, right? Now we want to know how long until they hit the ground. So we want to know time. So there are a couple methods that we can use for this. Whoops, 2 fingers. So first method, use the quad. Or second method, what we can do is we can solve for v final, then use v final to solve for time. Because in this scenario, this is one of those times where you don't have the right givens to solve it all at once using one of the 3 kinematic equations. So what we can do is you can use the vfy squared equals v naught y squared plus 2a delta y. Oh no, can't write over there. Oops. 2a delta y. Okay, zoom back out. So we can solve for that, solve for v final, then use that in vf equals v naught. Then we'll use that plus at to find time. So we can either go 2 steps or 1 step. I would prefer the 1 step, just use the quad. But remember, the quad is complicated, so you're going to have to go with what you're most comfortable with. So the quad is t equals -v naught plus or minus square root of v naught squared plus 2a delta y all over a. So one way or the other, we have v naught, a, and delta y. So we could do the quad, you just plug and chug, and it should work out. On number 2, the second method, we don't have all those. That's why you've got to solve for v final, then go for t. So let's go for the quad. I'm going to give, because that's the harder example. You guys could probably do the second method on your own. So let's work through this. T equals, so we've got -v naught. V naught is already -2, so that would give you a +2 plus or minus the square root of 2 squared, which is 4, plus 2 times -9.4, not 9.8, 9.4 4 times delta y, which is negative 500,000, all divided by negative 9.4. So this kind of stuff you can work through by doing the math and then doing your square root. So I will do that here for you. If you have a smart enough calculator, you can just plug it in and it'll go for you. So you've got 2 plus or minus the square root. So you would get 9.4 million. And those, you've got a negative times a negative, so that will all stay positive. Plus 4, so 9.4 million and 4. 9,400,004, all divided by negative 9.4. Now you will need the square root, right? We'll round that to 3,066. It's a few too many sig figs. 2 plus or minus 3,066 divided by negative 9.4. Now, time has to be positive, right? So if we're dividing by a negative number, we need a negative number up top. So we will have to use that minus on our plus or minus. So that would be 2 minus 3,064, which would be negative 3,000. Wait, I said that wrong. Oh, 2 minus 3,066 will give you negative 3,064 divided by negative 9.4. So you've got 3,064 divided by 9.4, give you 326. So 326 seconds to fall that distance. Okay. Now that's quite a ways to fall. I mean, falling for, what is that? 5.5 minutes. That's a long time to wait for the ground to come up at you if you've got no parachute. Now the second method, it should give you a very similar answer. There might be off by a certain amount, but as long as you're within 10% of the other method, then it's going to be sound. All right, so that's how you can find that one. You can do the second method on your own to double check to make sure that I'm not doing something wrong. Okay, let's go to the next example. Chris throws a ball vertically. Calculus ensues. So the position of a baseball tossed vertically upward is described by a function, y of t equals 1.5 plus 7t minus 4.909 t squared. Y is in meters, t is in seconds. So we've got 4 things to solve here. First, calculate the ball's initial speed at t equals 0. So how would we find the speed? If we have position here, right? This is position of a ball. How do we find speed? Well, remember we've talked about this before, where speed and velocity have this relationship, where if you take the derivative of position, you can get velocity. And if you take the integral of velocity, you get position, but we haven't done that yet. So let's take the derivative of this. So now if we were to take the derivative of y with respect to time, that would give you velocity. Now we're going to do the power rule. Now if you take the derivative of 1.5, that's just a constant. It has no variable, so that becomes 0. So we won't write that one down. Now the derivative of 7t, you take the 1 off your variable, you assume that t alone has an exponent of 1. So you bring that down, you've got 7 times 1 is 7. Then t to the 0 power would be 1. So you just have 7. I'll write that off to this side. C times t to the first. You have 1 times 7 t to the 0. Then you've got a bunch of 1s. You just get 7, right? Now let's do the next term. You have 4.909 t squared. So if we were to do this, you bring your 2 down times 4.909 t to the 2 minus 1. So t to the 2 minus 1 is just t to the first. So this would give you 7 minus 4.909 times 2 should give you 9.81. So minus 9.818 t. So that is our velocity function, right? Now, if we want the speed at t equals 0, we would take v of 0, which is 7 minus 9.818 times 0. That would give you 7 meters per second. Okay, so the hard part on there is just getting your velocity function. Plugging it into 0 is the simple task. So that was number 1. Number 2, it asks calculate the acceleration. So that means that we'll have to take the double derivative of position or the derivative of velocity. So if we take d squared y over dt squared, that would also be dv over dt, right? Take the derivative of velocity with respect to time, would give you acceleration. So if we're taking the derivative of this guy up here. Remember, derivative of a constant is 0, so that 7 goes away. Then the derivative of negative 9.818t, that t has a little 1 off to the side. So that 1 comes down, negative 9.818 t to the first, or I guess t to the 0, right? Because 1 minus 1 is going to give you 0. So if you have negative 1 times 9.818 t to the 0, 1 goes away, t0 goes away, you've got negative 9.818. I'll edit it out, or will I? So the acceleration there is negative 9.818 meters per second squared. And we know it's meters per second squared because in the problem up above, it does state y is in meters, t is in seconds. As you take derivatives, you're either going to divide by a time unit or you're going to multiply by a time unit, depending on if you're taking the derivative or the integral. Okay, so that was number 2. All right. Now, number 3, if we come back up here, calculate the highest point in the ball's flight. So think about how we would solve for that while I erase what's below here. Calculate the highest point in the ball's flight. So how would you know where to solve for that? That's kind of tricky. We have the position graph. So what you could do is you could graph that. You can see that this term is negative. So that would be a negative parabola. It'd be a concave down parabola. So you could graph that and try and find the height of that. Or we could take the derivative. So remember, taking the derivative is like finding the slope. So if we were to, we have that graph, right? If we want to find where the slope is 0, which would be at the top, let's just take the derivative and find where that function equals 0. So if we take the derivative of position, remember we get velocity, and at the peak of a flight, velocity equals 0 because you must change from positive velocity to negative velocity. So the highest point in the ball's flight, v equals 0 at the top. So we set velocity equal to 0. So we have 0 equals 7 minus 9.818 t. And we want to know the time that velocity equals 0. So let's add everything over and divide. So you've got 9.818 t equals 7. And then t equals 7 divided by 9.818 equals 0. We've got 4 sig figs on that, 9.818, so we'll go that far. So 0.7130 seconds. So that's the time it took for that velocity to reach 0, right? Now, if we plug that back in our position function, we can find the position at that time. So let's say y of 0.713. So we have 1.5 using the function up top, plus 7t minus 4.909. Oh, let's put our value in for t. 1.5 plus 7 times 0.713 minus 4.909 times 0.713 squared. That is a height of 3.995 meters. And to put our answer in the appropriate sig figs, that would be 4 meters. So at the top of the ascent, our position for that baseball is 4 meters high. Now, the last question says, was the ball in free fall, and can we use kinematics? So that's an interesting question. We assume the ball was in free fall because we weren't told the force of air drag, right? Because free fall means that there is no air drag. So if the ball is in free fall, then that opens way for us to use the kinematic equations. Also, to use kinematic equations, we need a constant acceleration. Now, if we look down here, as we take the derivative of position to get velocity, take the derivative of velocity to get acceleration, we see that acceleration is a constant line, right? It has no variable t. If it had a variable t, that means that it's changing as time goes on, and it would not be constant. But here, no variable t. That means that we're constant. Okay, our next problem, mail call. College is coming. A helicopter flying vertically is carrying a mailbag full of college acceptance letters for the Norman High AP Physics class. Measurements are made in meters and seconds. The height of the helicopter above the ground is described by the function h of t equals 3t cubed. After 2 seconds, the helicopter drops the mailbag. How long after the mailbag is dropped does it reach the outstretched hands of the class? So here, this flight has 2 sections, right? First section, we know the height with respect to time is given by 3t cubed. Then for the second part, we know that it would be in free fall. So what we know is a equals negative g, which should equal negative 9.81 meters per second squared. And it wants to know the time. How long after the bag is dropped does it reach the outstretched hands of the class? So let's figure out what we know. We have the position function. We can find the velocity function. So let's find the velocity function. That would be bring down that exponent times your coefficient, then decrease your exponent by 1. So that would give you 9t squared, right? So first, we need to figure out information on this first section before we can go on to the second section. So what we really need to know for this second section is the V naught, right? We will need to know the initial position, and we will need to know the initial velocity. We don't need to know anything else because it just needs to know the time after it was dropped. So we have the first 2 seconds, then how long after the bag is dropped. We already know the acceleration. It's in free fall. So let's find the information we need. What is the initial position on the second part? Well, that would be the position after 2 seconds, right? So let's say the height at 2 seconds would be 3 times 2 cubed. 2 cubed is 2, 4, 8. 8 times 3 is 24 meters. So that is the height at 2 seconds. So that would be our initial position for part 2. And we need the velocity at 2 seconds. We just got that function, 9t squared. So you have 9 times 2 squared would be 9 times 4, which is 36 meters per second. Okay, that's all we really need from the first part, because after 2 seconds, that function doesn't have any use for us anymore. Now, interestingly enough, the reason why we have to use a function instead of kinematics for that first part, if we take the derivative of that velocity with respect to time to get the acceleration function, you would have 2 times 9, and then t to the 2 minus 1 is 1. So then you've got an acceleration of 18t. That means the acceleration is not constant because it's changing every second, right? Because there is that t there. So that's important to know. That cubic function will give you non-constant acceleration. Now, we want to know the time it takes to reach the outstretched hands of the students. So we have y naught, we have v naught, we have acceleration. We do not have, oh, whoops, that dropped off there. We do not have v final. And we do not have time. So we ran into this before. If you don't have v final, right, let's write out our 3 oranges first. Orange 1, what order to put those in? V final equals v naught plus at. Then you have, I'll put this in terms of y. Delta y equals v naught t plus 1/2 at squared. Then you have vf squared equals v naught squared plus 2a delta y. So those are the equations that we can choose from. Now, we don't have vf, so we can't use this. Can't use the first one, and we can't use the third one. So we have to use the second one. Now, what you could attempt to do is solve for vf here, because you have delta y, you have a, and you have v naught. Solve for vf, then plug it into the first one, which is the second method from our first problem. However, you could go straight for the blue quad, or I guess in this case, we're not using blues. You could use the quad here to find your answer immediately. I did the quad the first time. This time I'll do the third orange up to the first orange, since that I did the other one last time. So we need v final squared equals v naught squared plus 2a delta y. Solve for v final, so just take the square root. And our v naught is 36, so we have 36 squared plus 2. Our acceleration is negative 9.81 because it's in free fall. And delta y, it is falling negative 24 meters. Don't forget your negative because it is falling. So v final, that is, calculator, type this out. We've got 36 squared is 1296 plus 2 times 9.81 times 24. That's 470.88. You can, those negatives will cancel out. So we have 470.88 plus 1296. Then we square root that number, 1766.88. If you take the square root of that, you get 42.034. We'll round that to 0.03 meters per second. Now we'll plug that in. We have v final equals v naught plus at. We're looking for t here. So we have our new v final. Let's solve for t. So we have v final minus v naught divided by a equals t. So we have 42.03 minus our v naught, which is 36, divided by negative 9. negative 9.81. Now, you can see here this is going to be an issue because I made a mistake. So let's look at my mistake. 42.03 minus 36, that's going to be a positive number. Positive number divided by a negative number, you can't have negative time. So up here, I did not think about that. The v final, it's falling, needs to be negative. It was under a square root, and every square root has a plus minus attached to it. It could be positive or negative. So that needs to be negative 42.03 minus 36 divided by 9.81. So let's do negative 42.03 minus 36. You get negative 78.03. Divide by negative 9.81. You get 7.95 seconds. So 7.95 seconds after the mailbag is dropped. Remember, we did not have to take into account the first 2 seconds in our calculation. 7.95 seconds after the mailbag is dropped, the bag of letters will reach the hands of the class. All right, those are our 3 example problems for this video. Next video, we will be going over the chain rule. Chain rule is a new way to take a derivative. If you've ever done the f of g functions, where you have a function inside of a function, we're going to take the derivative of those. So we're going to go over the chain rule next.